Okay, that's right, you guessed it. In today's video, I'm going to show you how to calculate the reactance of a capacitor in an AC source. And as a bonus, we'll talk about the relationship between the frequency of the source, the voltage source, and the capacitive reactance. Okay? So these are the two equations that we use to calculate the capacitive reactance. X is a symbol used for reactance, C is for capacitor, so we have capacitive reactance. In one case, we have the capacitive reactance equal to 1 over 2 times pi times F, the frequency of the source, the voltage source, times the capacitance of the capacitor. Or we can use this equation that the capacitive reactance is equal to 1 over omega, the angular velocity, times the capacitance of the capacitor. Now, before we begin, I just want to remind you that the capacitive reactance is the opposition to change in voltage across the capacitor. It's not really the resistance, it's the reactance, it's the opposition to the change in voltage. Some people say just it's the opposition to an AC voltage source, okay, or an AC current. All right, so let's just say, for example, that we have a capacitor that has a capacitance of 0.05 microfarads, and we have a voltage source that has a frequency of 100 kilohertz. That means when we calculate the capacitive reactance using this equation, the capacitive reactance is equal to 1 over 2 pi F times C. That's 1 over 2 times pi times 100 times 10 to the 3 hertz, because we have 100 kilohertz, times 0.05 times 10 to the minus 6 farads, because we have microfarads is 10 to the minus 6. And we get that the capacitive reactance in this case is 32 ohms. So for the first example, we use this equation. Now, we're going to do the same thing and use this equation, and we should get the same answer. All right? So we're going to do that on the next slide. First of all, I'd just like to point out how we get from 2 pi f c to omega c. Remember, omega is the angular velocity in radians, and there are 2 pi radians in a circle. T is the time, or in this case, because we're at capital T, it's the period, it's the time for one cycle. That's what omega is. It's the angular velocity. Velocity is distance divided by time, angular distance divided by time. And we also remember that the period, which is capital T, is equal to 1 over F, 1 over the frequency. The frequency and the period are inversely proportional. Now what I'm going to do is I'm going to substitute 1 over F into this equation for T, and I get that the angular velocity, omega, is equal to 2 pi over 1 over F. Now what I can do algebraically is multiply the bottom of this equation and the top of this equation, or this fraction, excuse me, by F over 1, and I simply get that omega is equal to 2 pi F. Okay, so there's two ways you can calculate omega. Omega is equal to 2 pi over T, but it's also equal to 2 pi times F, because the frequency and the period are inversely proportional. All right, so let's do the same kind of problem where we have a capacitor with a capacitance of 0.05 microfarads. We have the source. Now I converted the previous 100, kilohertz source. This would be the equivalent angular velocity, 6.3 times 10 to the 5 radians per second. And therefore we get that the capacitive reactance is equal to 1 over omega c, which is 1 over 6.3 times 10 to the 5 radians per second, times 0.05 times 10 to the minus 6 farad, once again minus 6 microfarads. And therefore we get the same answer, that the capacitive reactance is 32 ohms. Okay, in either case, whether you use this equation or this equation, the frequency or the angular velocity, then you should get the same answer. All right, now I just want to go over the relationship between the frequency and the capacitive reactance. You'll notice in this case, the frequency is on the bottom half of this equation, this fraction, excuse me. That tells you that the frequency and the capacitive reactance are inversely proportional. The capacitive reactance is inversely proportional to the frequency. That means as one goes up, the other goes down. For example, if we increase the frequency, then the reactance, the opposition is going to decrease. And if we increase it enough, then the capacitor begins to act like a short circuit, like a wire. Okay? If the frequency decreases, then because it's inversely proportional, the reactance, the resistance, the reactance of that capacitor is going to increase. And at some point, if we increase the frequency, if we decrease the frequency enough, then it begins to act like an open circuit and no current can flow through it. All right? So there we go. Those are kind of the three things I wanted to do. Show you how to calculate the capacitive reactance using this equation, and then go over the relationship between the capacitive reactance and the frequency of the source. Thank you very much for watching. I hope you found it helpful. If you did, please do all the following three things. Subscribe to my channel, give me a thumbs up for this video, and leave me a nice positive comment in the comment section below. Thank you very much for watching. We will see you in the next video.